0 Kelvin, so absolute zero, is not reachable no matter how hard you try. But why is that the case? To understand this, we have to dive deep into thermodynamics. Okay, so as a start, I think it might be useful to understand why there even is something like 0 Kelvin. So why is there an end to the temperature scale? On the atomic level, temperature is nothing but particle motion, and obviously there will be a point when no particles move at all, and this theoretical point is called 0 Kelvin, so absolute zero. There can't be less particle motion than no motion at all, and this is why there must be an end to the Kelvin scale. So there is a point which is 0 Kelvin, and in Celsius that would be about -273 Celsius. And now there's a popular statement which says that you can never really reach 0 Kelvin. So you can draw closer and closer and closer and closer to absolute zero, but with a finite number of steps you can never really reach 0 Kelvin. And to understand why this is true, let's maybe first talk about the third law of thermodynamics. The third law, or also often dubbed the Nernst theorem, talks about the entropy of a system at 0 Kelvin. And it states that the entropy of a system at 0 Kelvin always equals one specific value. So there can't be two different systems who both have 0 Kelvin temperature and who have a different entropy. So entropy is a fixed number at absolute zero. And to give you some kind of intuition maybe why that's true, let's maybe look at the definition of entropy, at least at one of them. There are many definitions, but I'll choose the statistical one in that case. So it says that entropy equals the Boltzmann constant times the natural logarithm of S. So what is S? Basically S is the number of states a system can be in, the number of different states a system can assume. And with a temperature above 0 Kelvin, these particles of the system are wiggling, so there are many states they can occupy. But at 0 Kelvin the particles stop to wiggle, so there's only one state they can be in, and this state is standstill. That's why in that case S equals to 1, there's only one possible state, and that's why always our entropy at 0 Kelvin equals a certain constant which is fixed. Step 2 in understanding why absolute zero is not reachable. We have to understand why thermodynamical processes can always only be isentropic or isothermal, but never both. By the way, an isentropic process is a process where the entropy doesn't change, so where there's no heat put into the system from the outside world or reverse. And an isothermal process is a process where the temperature of the system stays the same all over the process. So we need these two terms now to understand why we can never have both at the same time. Okay, so the amount of energy which is added or subtracted to a system during a process always consists of two factors. The first one is heat, and the second one is work. So heat basically means, is my system thermally isolated from its surrounding? If not, there can be heat flow. And work means, am I, for example, compressing or decompressing a fluid or a gas? So these two factors play into the total amount of energy which is added or subtracted to a system. Okay, so now why can't I have isothermal and isentropic at the same time? Well, isothermal would mean that the temperature of my system stays the same, so that the total change of energy is zero. That would mean that my heat energy is equal to minus the work done. And assuming I also would want my system or my process to be isentropic, that would mean that also my heat energy, so the change in heat, the heat flow, would have to be zero, because isentropic means that there is no heat exchange with my surrounding. And that would automatically mean that the work done is also zero. But that means there's no heat flow and there's no compression or decompression, so basically nothing happens. So I can only have isentropic and isothermal at the same time when nothing happens at all, and that doesn't make sense. So I cannot have isentropic and isothermal in a process where I want something to happen. Okay, so now in step 3 we can put these pieces together and ask ourselves, why can we never reach 0 Kelvin in a finite number of steps? And let's maybe do this by first drawing a temperature entropy diagram. And let's maybe also add two different systems which start at different entropies. And now I'm trying to cool them both down to at least theoretically 0 Kelvin. And as we know, the entropy at 0 Kelvin is one fixed value. So these two systems would go to the same entropy in this diagram. But now, as we've learned before, we can only make processes which are either isentropic or isothermal, which means I can only move in horizontal or vertical lines in my diagram. So, for example, when trying to reach 0 Kelvin with my system number 1, for example, I can only move horizontally or vertically. And that would mean I can never really reach 0 Kelvin, as you can see in the diagram. The problem is that in order to reach 0 Kelvin, I would have to move smoothly between my two curves. But I cannot move smoothly. I can only move either isentropically or isothermally, but never both at the same time. And that's the problem. I can only move left and down, left and down, left and down. And that's why, and I think that's obvious with this diagram as a visualization, I can never reach 0 Kelvin. So I can come infinitesimally close, I can come as close as I want to, but I can never really reach this point at the end. And that's why 0 Kelvin in reality will never be reached. Right, so that was obviously an oversimplified version of why this statement is true, of why the third law of thermodynamics holds, and of why we can never really reach absolute zero. But I think it's still nice to have some kind of intuition behind this statement. So if you have any questions, please put them in the comments. If you have any recommendations for upcoming videos, also put them in the comments. And if you have been, thanks for watching.